Example. The radius of a sphere is increasing at a constant rate of 0.1 centimeter per second. How fast is the volume increasing when the radius is 10 centimeters? Please note that V, the volume, and R are functions of the time. So when we differentiate V and R, we have to take this into account. The only thing that is always true is the connection between V and R. V is the volume of a sphere. It equals 4 over 3 pi r to the power of 3. Differentiate both sides with respect to t, and we get dv dt equals 4 pi r to the power of 2 dr dt. Now we have to focus on the snapshot. We read again the problem and we see what we need to substitute. First of all, the radius of the sphere is increasing, so it means the dr dt is positive. Constant rate of 0.1 centimeter per second. It means the dr dt equals 0.1 centimeter per second. Then we read that we need to focus on this instant at which the radius is 10 centimeter. It means that r should be equal to 10 centimeter. We substitute everything in, and we get that dv dt equals 4 pi 10 to the power of 2 times 0.1 centimeter per second. And we get the dv dt equals 40 pi cubic centimeter per second. I would like to know that you can check the units if you write in units as I did in this problem. If you look, the units are centimeter to the power of 2 times centimeter over second, which is really cubic centimeter per second. It's a really nice way to check your math. Now we can answer. The volume is increasing at the rate of 40 pi cubic centimeter per second. Example. Air is pumped into a spherical balloon at a constant rate of 2 cubic centimeters per minute. How fast does the radius of the balloon increasing when the radius is 6 centimeters? V and R again are functions of the time, and it is always true, again, that V equals 4 over 3 pi of r to the power of 3. And as before, we are differentiating both sides with respect to t, and we get exactly as before. And now we want to focus on solving for dr dt, because now we have to solve, because we are asked about the rate of change of the radius. And we do the math, it's not very difficult, and we found that dr dt equals dv dt over 4 pi r to the power of 2. Now we can do the snapshot. This is dv dt. And this is r at this specific instant. So we have to replace r by 6. And here's the equation. We are replacing the r by 6, dv dt by 2, and we get 1 over 72 pi. And the answer is that the rate of change of the radius is 1 over 72 pi centimeter per minute. Here are general steps for related rates problem. It has two parts, the always true and the snapshot. In the always true, first we have a good drawing and we label everything, and we noticed what is given with respect only to the always true. Then we have to find the main equation that will connect all the variables. Then we are going to differentiate, and don't forget to use the chain rule for all those amounts that are dependent on time. Not all amounts may be dependent on time, so please notice which one are and which one are not. If you want, you can solve now for what you want, like in the last problem we were solving for dr/dt. In the snapshot, you will like to substitute all the numbers. Or you can first do the draw label and given to find the main equation, to differentiate that, and in the snapshot to substitute everything and then to solve for exactly what you need to find. I will always definitely prefer this way. The most problematic part in related rates problems is to find out what is belonging to the snapshot, to the instant, and what is always true. By doing this, I never get into trouble because I'm going to substitute and solve and do everything in the snapshot already. Be careful. Always true is also true in the snapshot. This is also true here. But the snapshot should not be always true. It is true only for a very short instant and cannot be always true. So this is not true. In example that we did, what is always true? And what is true in the snapshot? If you read carefully, air pumped into a spherical balloon at a constant rate of 2 cubic centimeters per minute. So dV/dt is 2 cubic centimeters per minute. This is also true at the snapshot. Also at the snapshot, R equals 6 centimeters. R is not 6 centimeters at the always true, because R changes with time. Be careful again. All the steps in always true, including the drawing, should not use any information from the snapshot. This is the most common problems in related rates. Example. Again, look at this problem. Air is pumped in the spherical balloon at a constant rate of 2 cubic centimeters per minute. How fast does the radius of the balloon increase when the radius is 6 centimeters? This should be the right drawing in the always true. This is wrong. You see that the radius is 6 centimeters, but this drawing is only true for a very, very short instant. It's not only that it's wrong, if you do it, you will never get a related rate problem. If you fix the radius and the radius doesn't change, then it makes totally no sense in this one. But in a very complicated problem, sometimes it's really very hard to distinguish between the snapshot and the always true, and you have to be very careful about that. Using constants from the snapshot in the always true is the most common mistake and should be avoided by substituting whatever possible in the snapshot step.